Hello and welcome guys. So in the last video, we completed this version 1 of this project series. So in this version 1, what we did, first we computed our vocabularies using this TensorFlow text vectorization. After computing this vocabularies, we are converting this each word into numbers. This is basically the index of each word present in the vocabulary list. Okay. So this process in the terms of generative AI, we call this process as a tokenization. Okay. So we are tokenizing it. And after that, we are initializing our TensorFlow embedding layer. So here we are not passing any information. So we are saying that randomly initialize this embedding. Okay. And after initializing this embedding, we are creating this sequential model. And in this, we are adding our vectorized layer, embedding layer, followed by this LSTM layer and dense layer, and we are training our model. And after giving this X and Y's, we are updating the weights, we are updating these weights of this hidden layers and this LSTM layers, and also this embedding layer. Okay, so we are training like this and we are getting this result. Okay, so in this video, what we are going to do, in this video, we are going to use some other technique to perform embedding. Okay, that technique is called Word2Vec. So Word2Vec is very popular technique and it's a very powerful technique, we can say, to create embedding of words. Okay, so embedding is very important thing, because if we are not able to perform right embedding, then we will end up with wrong model, and that will not be that much perfect. Okay, so embedding is very important thing in any NLP use case. Okay. So first, Word2Vec is a technique to represent word as a dense numerical vectors, which is called embedding, such that word with similar meanings appear close to each other in the vector space. Okay. So basically, we are going to convert this words as a vector. And once we plot that vector in the vector space, then we want this embedding in such a way so that words with similar meaning are close to each other. So that we can say that, okay, so like if I'm saying king and queen, so king and queen are somewhere similar to each other, like in some perspective. Okay, like both are royals, or you can say both are rich and powerful, something like that. Okay, and later if we train our model, so then model also understand, okay, so these are the words which are close to each other, so I have to remember these things. Okay, and this, why this embedding is important, we already know that any machine learning deep learning model understand numbers, take numbers as an input, we don't take any text information, so we have to create a robust embedding for that. Okay, so what is this Word2Vec? So first, Word2Vec is this type of thing. So it's a neural network. Okay, and it is a shallow neural network. Why it is shallow neural network? Because we have here only one hidden layer. Okay, that's why we call this Word2Vec as a shallow neural network. And this is trained on large corpus. Okay, so this is a simple thing. And the core idea is what? Core idea is that word that appears in similar context having similar embeddings. Okay, so we have to compute embedding in such a way so that if word is very similar to each other, then it has to be approximately similar embedding. Then only it will come close to each other. Okay, so that is the core idea of this. And in this Word2Vec, we have two types of architecture. First is continuous bag of word, and second one is Skipgram. Okay, so here we have two different types of approaches to create embeddings. So let's see first what is continuous bag of word. The aim of continuous bag of word is that it has to predict the target word given its surrounding context word. Okay, so like if I want to predict this WT, so I have to give some surrounding words like WT minus 2, WT minus 1, WT plus 1, WT plus 2. Okay, in the architecture, I will give surrounding word as input and I will try to predict the target word. Then that architecture is called continuous bag of word. Okay, so let's take one example here, like the sky is blue. Okay, and here I am taking this window size as 2. So window size I am taking as 2 and I am taking target word as sky. Okay, so sky is my target word, so it will be my y, And what will be my x? So x will be, first x will be the, and then x will be is, and also there will be blue. Okay, why? So from here I will see, I will go 2 step backward and 2 step forward. So if I'm going 1 step backward, then I'm getting the. If I'm taking one more step here, so if I'm going 2 step backward, then there is no information, so I'm only considering the. And if I'm going 1 step forward, then I'm getting is, and if I'm going 2 step forward, then I'm getting blue. Okay, so here my window size is 2, so I can go maximum 2 step backward and 2 step forward. Okay, so this is all my x values. Okay, so this is my x and sky is my y. So here my x will be the is blue. Okay, and my y will be sky. So this will be my x and y, and I have to train this model and in such a way so that after giving this as input, I get this as output. Okay, so after giving this as input, I get this as y output. So we get some embedding here. We update this weight, and finally whatever final weight we got, that will be our embedding. Okay, so here uses surrounding words to predict the center words. Context words are usually averaged, work faster, and performs better for frequent words. So these are some key points. I will explain you each points in detail, why it works faster and why it performs better for frequent words. Okay. So first understand that we have to give this. Suppose this is our sentence. So in this sentence, we first select some window size, and based on that window size, we select the target word, and according to that target word, we take to whatever is the number of window size, we take that step backward and that much of step in forward direction, and we pick all the words and we make those words as our context word, which is our x values, and we tries to map it with the target word, and we tries to learn the embedding. Okay, so this is how continuous bag of word works. Okay, and one more thing here, why it's called continuous bag of word? Because here if you see this, the is blue, we are randomly putting this here. We can also start from here, or we can put like is blue and then the. Okay, so we can shuffle it, and we can randomly pick anything, and we can put here and start from here. Like we can start from wt plus 2, wt plus 1, wt minus 1, wt minus 2. Okay, there is no any order maintained here. Okay, that's why it's called bag of word. And second one is this skipgram. So in skipgram, we predict the surrounding context word given the center target word. Okay, so in this, we take this sky as input, and we tries to predict these surrounding words. Okay, so suppose here I'm taking window size as 2, center word I'm taking as sky. So this will be my x, and my y's will be sky. The sky is sky blue. So I will take from here, I will go 2 step backward, 2 step forward, and whatever pair I will generate, that will be my y's. Okay, so here if you see this example, so here we have this wt as input, and we are going to predict wt minus 1, wt minus 2, and wt plus 1 plus 2. Okay, so this is how we are going to do these things. Okay, so here how we will train this skipgram. So we'll give some like wt as input, and we'll get this output, and so initially we start with some random weights, and we'll get something, and based on that we compute the loss, and we'll update this information, we'll update these weights, and after that, once our final training is completed, after that whatever weights we'll get, that will be our embedding. Okay, so this is how we'll train this thing, this skipgram. So this skipgram, in this skipgram, what is the characteristic of this skipgram? Each word act as a center word, generate multiple training pairs, perform better for rare words, more computationally expensive than continuous bag of word. So if you see, continuous bag of word perform better for frequent words, and skipgram perform better for rare words. And continuous bag of word is faster, skipgram is little slower and expensive. Okay, so now let's understand why this continuous bag of word is better for frequent word and why Skipgram is better for rare words. Okay. So let's take one example here. Same example, the sky is blue. So these are my context word. These are my X values and this is my Y values for continuous bag of word. Okay. So if you see here, this the is off. This appears more often test target. Okay. So if something is frequent words, so frequent words are like the is of, these are some frequent words present in the corpus. In any corpus, you will see these words. Okay. So it means that probability of these words coming at the Y is high. Okay. If I take this example, the sky is blue. This the will get one chance to come here as Y, and then sky will get one chance, is will get one chance to come at Y, blue will also get one chance to come at Y. So it means that frequent word will get more chance to come at Y. Okay. So if they are getting more chance to come at Y, then it means that according to that word, this weight will get updated more number of times. Okay. So whatever X will get, based on that will get some Y, and based on that Y, this model will get updated. This model's weight will get updated. Okay. So it means that frequent words, according to frequent words, weight updates will be more. Okay. So that is what I have written here, that these words receive more gradient update. So rare words are updated less frequently. So it means that if there is some rare word, if it appears only 10 times or 5 times, so it will get only 5 times to according to which this entire neural network's weight will get updated. Okay. So that's why I'm saying here that continuous bag of word embeddings are biased towards frequent words. Okay. So this is the key insight of continuous bag of word, and this is a very you can see very frequently asked interview question, that explain how continuous bag of word is biased toward frequent words, or it is more better for frequent words, and why Skipgram is better for rare words. So these are very important things you have to remember. So this is how continuous bag of words works better for frequent words. Now let's see how Skipgram works better for rare words. Suppose if we have some rare word in our corpus and we want that our model focus on that rare word. So how Skipgrams work in that direction and how it focuses on rare words? Let's see that. So we know that in Skipgram we predict the context word from the center word. So here our center word will be sky, and we are going to predict this the is blue, because these are the surrounding words of this sky. So our aim is to predict these words. Okay. So in this, every word become a center word. Every word will get one chance to become a center word. Okay. So every rare word generate this center context pair. Okay. Okay. So now let's see how this Skipgram focuses more on rare words, and it gives more importance to rare words. So let us assume that here this blue is a rare word. Okay. So this blue will be part of here. If I take this example sky, so here blue is in Y. Okay. So this is my Y and this is my X. So at output layer, this blue is there. Okay. For this example where our center word is sky. Okay. Let's take another example where our center word is. So there also this blue will be part of Y. Okay. If I take another example somewhere, suppose we have some other word after this blue. So for that word also this blue will be a part of that Y. Okay. So what I'm saying here in Skipgram, we are getting this word more number of times at Y, and based on this blue also there will be updates happening. Okay. So this blue will be, this rare words will be more number of times at output layer as compared to here in continuous bag of word, where rare words is only appearing one time. Okay. How many number of times that rare word is in the corpus, that many number of times only that word is getting appeared in the Y's, and according to that word weight updates is happening. So suppose if some word is appearing 100 times, okay, 100 times, then only 100 times this weight update will be done according to that rare words in the continuous bag of word. Okay. And in Skipgram, what will happen? Suppose that rare word is appearing 100 times, and if I am taking window size as 5, and let us assume that we are getting 10 training pairs for each word. Okay, like here for blues, we are getting, in this example, for blues, we are getting 2 pairs. One is with sky. So with sky also I'm getting blues in Y's, and with is also I'm getting blues as here in Y's. Okay. So similarly, let us assume that for each word we are getting 10, approximately 10 training pairs, where we are getting rare words in the Y's of this X and Y pairs. Okay. So for 100 words, we will get 1000 updates. Okay. Here we are getting for 100 words, we are getting only 100 updates, because only in 100 possibilities, this rare words is getting chance to come at output layer. Okay. At output, which is our Y. And here it's getting 100 multiplied by that many number of training pairs which we are computing using our rare words. So which is here, if I am assuming it as 10, so it is 10 multiplied by 100, which is 1000 times that rare word is getting chance to come here, and based on that this weight is getting updated. Okay, so we can say that rare words receive stronger learning signals. Okay, and why continuous bag of word emphasizes frequent word? Because rare words appear less often as target, fewer updates, weaker embeddings. Context averaging also causes frequent words to dominate. Later we also perform context averaging by multiplying these weights and summing it. So weight averaging we are doing also. So there also those weights dominates, those frequent weights dominate, and that will overshadow these rare words. Okay, so rare words get smoothed out. Okay, so this is very important thing, that Skipgram is preferred when learning high quality embeddings for rare words. Suppose your corpus contains some technical information, okay, some technical jargons which you want your model to remember. So in that scenario, you have to go with skipgrams. And if the continuous bag of word is preferred when speed and frequent word accuracy matters. Suppose you have more frequent words, there is very less rare words, and you also want speed. Okay, so you want to train your model fastly, and so where speed matters, then you have to go with continuous bag of word. So how this continuous bag of word is faster? Here we are computing our embedding, one hot vector representation we are computing, and we are passing here to the hidden layer, and here we are computing our logics. Okay, based on that loss we are updating our weights. Okay, and here what is happening, here we have 1 2 3 4 different logics we are computing, and based on that 4 times we are computing softmax score. Here we are computing 1 time softmax score, and we are updating the weight. Here we are computing 4 times softmax score, and we are comparing it with the output layer, and we are computing the loss, and we are going backward and updating the weights. So that's why skipgram is slower, because it is much more expensive at the output layer. Okay, here we have only one vector, and here we have multiple vector. So that's why at the output layer it is more expensive as compared to continuous bag of word. That's why skipgram is slower as compared to continuous bag of word. Okay, so this is, I think this is all about continuous bag of word and skipgram. So I hope you understand in detail how skipgram works and how continuous bag of word works. Now let's see how we can implement this. So to implement this, we can use this Gensim library. So using this Gensim library, you can call your Word2Vec like this. From gensim.models, you can import this Word2Vec, and here you can, if you want to train your model, then you have to pass your words as an input, which is a, you can say, which is a list of word you have to pass as input, and you have to define some vector size so that your embeddings will get created based on that vector size. And you have to give some window size, as we discussed that we need some window size, and workers and all you can give. like how many CPU processor you have and all. And also there is one more parameter which is SG. So SG, if you give SG as 1, then it means you want to use Skipgram architecture. And if you give SG as 0, then it means that you want to use continuous bag of word architecture. Okay. So this is how you can train your model, and you can save your model like this, model.save Word2Vec.model. If you do, then you will be able to save this model. Okay. And if you want to load this model, then you can load like this. So this is how you can train your model. And if you want to vectorize any word, then you can use like this model.wv, and you can give your word as input here, and you will get here vector. Okay, so this will give you numpy vector of this word. Okay, and if you want to do similarity search, then you can do like this model.wv.most similar, and here you can pass your computer. So this computer, so I want most similar vectors close to this computer, and I'm giving here top n as 10. So I want top 10 vectors. So it will give you top 10 similar vector which is similar to this computer. Okay, so this is how you can do similarity search, and this is how you can vectorize any words. So this is how Word2Vec works. Okay, so using Gensim you can easily access Word2Vec, and also Gensim have some list of model present, so you can also use some pre-trained model. So these are some models, like this is trained on Google News dataset, and this is a Wikipedia news dataset. This is trained on that. So we have different models. We have some model which is trained on Twitter dataset. So you can use these models also. So Gensim provide you some pre-trained model also, or you can develop your own model by giving your own corpus. You can train and get a new model also. So you can use that. You can access Word2Vec from Gensim. And if you want to learn more about Word2Vec, then I find this tutorial very good. So you can go through it, and you can learn more information like what is continuous bag of word and skipgrams. So this, I already showed you this examples, that how training pairs are getting calculated, and here they have also given you very good implementation, so that you can implement this continuous bag of word and this skipgram from scratch. Okay, using Tensorflow, you can take this Shakespeare data set, and you can calculate this text vectorization, and you can compute this entire thing. Okay, this entire Word2Vec from scratch. Okay, so you can go through it, and you can learn more about Word2Vec. Okay, from here. Okay, so I think we understand this Word2Vec in detail in this video. So now in the next video, what we are going to do, in next video, we are going to improve this version 1, and we are going to develop version 2 of this project series, where we are going to use Gensim library, and we are going to train our own Word2Vec model, and we are going to use that Word2Vec model in this architecture, and we will try to improve this architecture. Okay, so I think that's all for this video. I hope you like this video. Thank you guys. Thanks a lot for watching this video.